this is John Black, Superchemist. We're here to talk about alpha bromination of a carbonyl compound. And we're specifically talking about making bromoacetone. The whole reason why this reaction works, here's the equation. Got your acetone, bromine, some type of protons, I have acetic acid, and this will add on the bromine on the alpha position. Now, how does this happen? This alpha ketones, they tautomerize into enols, all right? And here's an example of it. You can think of it as an internal thing where this hydrogen down here jumps up on the oxygen and makes a alcohol, and the double bond, is split down here. I mean, actually, the electrons here, this going to here, and these electrons will go down to make the double bond. This double bond will go up on top of there. So you have a neutral enol, okay? So it's an alkene and an alcohol, an enol. This is what makes your reaction. Most times, though, you only have this in solution. You have very little enol without some type of acid or base. Okay, you can't use a base because it over bromates or over halogenates. And it also, with this specific example, because you have methyl groups on both sides, you would do the haloform reaction. So we need to use protons. We need to use an acidic environment so that we can make a lot of this enol instead of just a little bit. Let's go over the mechanism. Like I said, enols are spontaneously made, but very little usually in solution. Unless, like I said, you have acid or base. Here's our acid, sulfuric acid. It's going to protonate the lone pair electrons, and you'll have this alcohol thing here, but you're making an oxonium ion. This oxygen is positive. So you have a base, you need a mild base, like say the hydrogen sulfate, anion, or the water that's in there a little bit, or even an OH, because water ionizes, right? Any of those things in there, lone pairs, can come and grab the hydrogen, the electrons fall in to make the double bond, and this double bond goes up onto the oxygen. You end up with your enol, okay? Which is a neutral compound, right? Because you added a proton, but then you took it back, right? So you recreated your sulfuric acid. You only need a catalytic amount, right? Because you can see you're remaking it. So anyways, here's your enol can go, resonate back and forth in between these two structures, right? You could have the electrons jump down, forming your double bond again, and this double bond goes out here to your empty orbital. So now you have a tetrahedral here, you have your double bond here, but now you have an oxonium ion. You know what I mean? The whole ion overall is neutral, but you have negativity here and positivity there, like a Zwitter ion. So you can either think of this is what's going to react. This is your nucleophile. This is your negative part. The positive part comes from the bromine. And you can think of either one of these resonance things. Either the double bond comes out, these electrons jump down here, and this double bond attacks the bromine, right? Or you can say this does. It comes up, attacks the bromine, and you're left with a negative bromide. Here's your negative bromide. Here's your acetone. Remember the electrons came down to form the double bond. This double bond jumped on to grab, opened up to get this bromine. So now you have a positive over here, oxonium ion, and you have your negative counter ion, your bromide. So it just works off this hydrogen, so that this becomes neutral. And then you end up with HBr, an acid, and you end up with your products, right? And you can see, we up at that first step when we protonated and deprotonated, we just basically recycled our sulfuric acid that we put in there. Or I guess it would have been acetic acid. Whatever acid you chose. You know what I mean? It's replenished. But not only that, you make extra acid down here on this step. So this is autocatalytic, you know, the reaction. You really don't need that much acid to catalyze this because you're actually making acid as the reaction progresses. Now you can see how it forms the phenol. Here's the equation. Add the B up. Here's the enol. How do you know? Let's say you had an unsymmetrical ketone. Now, where would the bromine add? Would it add here, or would it add here? Well, it would add here on a more substituted side, just from. That's the intuitive thing, and also the reason why is because of this enol formation. The enol, the double bond, according to Zyseff's rule, right? Zysef says he's going to. Over here, it's not as substituted. Over here, it's substituted more. You got one, two, you know what I mean? You got this group here. If I put the double bond over here, there's nothing on this side. It's not substituted at all. So obviously, this is going to be where, and this is where the electrons come out of. You know what I mean? Right here. And on the other resonance form, they come out right here. So this is where you would add your bromine. See, on the more substituted side. Now, if you use a base here, okay, even if you had no methyl groups, and you didn't have to worry about the haloform reaction, okay, have it like this. You will never substitute twice on the same side, okay, if you have an acid. See how you can do that? This will never happen with two bromines on this side if you use acid. Now, if you use a base, it'll keep going until it, until it has no more hydrogens to pluck off of it, right? But an acid, you can only have one. Now, I'm not saying it can't attach another bromine over here, but if it does, that's all it will attach. Even though there's another hydrogen left, right? There's another hydrogen right here. It won't pluck that off and add another, bromine. It will only add one. So if you put excess bromine in, twice as much as you need, one will add here and one will add here. If you only add, enough for one, it'll always add just on the one side. I mean, not always, you know how chemistry is. You're making 50 million zillion byproducts or whatever. But in general, the majority will be one addition on one side. If you had double bromine, it would be one addition on each side. Alright, so like I said, it likes acidic conditions. It limits the, only one alpha addition with each halogen, for each side. Like I said, if you put in double the amount of halogen you need, you're going to get an alpha on both sides, an alpha addition on both sides of the carbonyl, most likely, I guess. If you mix bromine and acetic acid, you get no reaction, okay? And the third thing I wanted to bring up is that you want to keep the temp below 10 degrees Celsius. Use an ice bath. Get this stuff, when you first start out, get all your chemicals as freezing cold as you can, 5 Celsius if you can get it that low. And then try to keep the reaction below 10 C the entire time. Now let's go over how I want to try this reaction. Keep in mind, this is a tear gas lacrymator. It's terrible. You ain't going to want to, breathe this stuff or have it touch your eyes or anything. Because it's going to react, it's going to burn, it's going to burn your eyes, it's going to be terrible. It's the worst kind of tear gas you could have, man. So I want you to keep in mind when I do these videos in the summertime, where there's no experiment. The reason there's no experiment is because I've never done it before, and I'm guessing on a lot of stuff, like here. And I did a 3-part video on methamphetamine and synthesis via reductive amination. Now the instructions in that video are dead on, But then I go into some guesswork about how you can get rid of the water to get a better yield. Okay, get water out of the pot. So they'll push so you can't, the imine will turn into the hemiaminal and back and forth. Well, it can't turn into an hemiaminal if you don't have any water in there. So if you get the water out, you get a better yield. So I go over all these stuff like anhydrous salts, molecular sieves, but then I mention using a Dean-Stark apparatus and using benzene as the solvent instead of methanol. Now, that was a guess, and I say in there that I am guessing, you know what I mean? It's not like I'm saying this is a fact. Anyway, since then I found out that you need protons in the reaction mix or the reaction won't work. So if you replace methanol that has protons with benzene that has no protons to come off, the reaction won't work. And so using a Dean-Stark apparatus is irrelevant, okay? But I wanted to mention that because, this is a guess right here. I mean, everything I said beforehand, I try to say in these videos which is guesses and which is fact, you know what I mean? So far, everything in this video is a fact. Now we're getting to the guesswork because I've never done the experiment. If I did the experiment, I would film it and have it on here. You know what I mean? The reason why I don't is because I never did it. So I just want you to keep that in mind, you know what I mean? These are just ideas I have. This isn't factual here. This is just guesswork. Okay? So anyways, the way I would do it, I would set up so that I can drip stuff in, have an equalizing funnel, not a step funnel, an equalizing funnel, and have a condenser, water-cooled condenser, to, any fumes that come off, and I'd lead a hose to a suck-back trap and a bubbler, and I'd have the acetone in here, I'd have the bromine in here, and my original thought was to use acetic acid because that's, I think, the choice of most chemists would be, acetic acid. But in this case, the boiling point of what we're making is very close to acetic acid. So when you get done, trying to separate these two things may be hard, okay? So I switched my idea. Instead of using this as a solvent and an acid, I decided instead I will use sulfuric acid, okay? So I would cool everything down. You want this to be, 10 degrees Celsius or lower at all times. So I would put my acetone in the freezer and put the acetone in here. I'd chill everything down, bromine and the sulfuric acid. The bromine, now as you do this reaction, it's going to take a while. So your bromine is going to warm up in the meantime. You'll have an ice bath for the pot, but the bromine is going to warm down. So what I would do is I just put a little bit of bromine in, let it drip, and then when it ran out, I'd open this up real quick and dump some more bromine in there. Having the bromine in the freezer, chemical freezer, not your food freezer, so that it doesn't warm down during the reaction, you know what I mean? So I would have a little bit of bromine in here, put all my acetone in here, and when I was all ready, I'd put a few milliliters of sulfuric acid in as a catalyst in here. Then I would drip the bromine into the pot where the acetone and the sulfuric acid is. I drip it in slow, like I was titrating. Now, you drip it in and it gets a little bit red, and then it reacts and the red goes away, right? You want it to go back and forth from red to clear, you know what I mean? You don't want it so fast that you flood the reaction with a bunch of bromine. You want it to react as it's dripped in, kind of. At least that's my guess. Like I said, keep it below 10 Celsius. Even if you have to stop the reaction, you know what I mean? Let's say your reaction's getting to 10 degrees Celsius, then you stop putting the bromine in, you know what I mean? You wait for the pot to cool back down. This is a 1-to-1 ratio on the bromine and the acetone, but I would probably put in more acetone than bromine. The reason why is because you might have the bromine, it can only attach one time